And welcome to this explainer. I am so thrilled to have you here today because, well, we're about to embark on an absolutely mind-bending journey. Seriously, we're going to shrink ourselves down way past the classical world we know, the world of falling apples and orbiting planets, and dive headfirst into the totally bizarre, logic-defying quantum realm. But hey, don't worry, I promise we won't get stuck down there. We're going to travel from the most abstract philosophical puzzles of the universe right back out to that very tangible smartphone sitting in your pocket right now. It's going to be a wild ride, so let's get started.
All right, here's a quick look at our roadmap for today. We'll kick things off with the quantum world's rules, then tackle the measurement problem, move on to Einstein's spooky action, and wrap it all up with real-life quantum technology. Easy enough, right? Let's dive in.
Okay, part 1. The quantum world's rules, leaving the classical world behind.
So imagine mentally shrinking yourself down past a grain of sand, all the way down to individual atoms. Down here, the predictable classical physics of Isaac Newton, where a billiard ball moves exactly as you'd expect it to, it just completely stops making sense. Instead, we enter the quantum world, and out here, everything is probabilistic. Energy and matter, they exist in these tiny, quantized, discrete little packets. And rather than acting like a totally predictable billiard ball, a quantum particle acts a lot more like rolling dice. Its exact state is just completely unpredictable until the exact moment you measure it.
Now, as you can imagine, this realization didn't exactly happen overnight. It took some brilliant minds slowly peeling back the layers of reality. Look at the timeline here. In 1900, Max Planck figured out that energy relates directly to frequency. Then, boom, 1905, Albert Einstein proves light isn't just a wave, it's actually a stream of tiny little particle packets called photons. Fast forward to 1913, Niels Bohr realizes electrons only hang out in very specific, discrete orbits. And by 1925, Werner Heisenberg was mapping out these bizarre particle jumps with some incredibly complex matrix math. Basically, they were all discovering that energy and matter are connected in some really strange ways.
And right at the heart of all this weirdness is a massive buzzword you've probably heard: wave-particle duality. Thomas Young's famous double-slit experiment perfectly grounds this whole concept. So picture this. You're firing single particles of light, photons, through a solid barrier that has two little slits in it. Now, if light is a solid particle, you'd logically expect to see two distinct lines on the wall behind it, right? But nope, the light actually behaves like a wave, creating this huge, complex pattern of interference bands on the wall. But here's the kicker. When it actually hits the screen, it hits as individual, discrete dots. So it's behaving as both a wave and a particle, completely depending on how we measure it. Crazy, right?
Which perfectly sets us up for a concept that just completely defies human intuition: superposition. Let me just ask you this. How can a single particle possibly be in two places at once? Well, in our normal everyday world, it can't. But down in the quantum realm, it absolutely can. You see, before we measure it, a particle's properties, like its location, speed, or spin, exist in this hazy mathematical state called a wave function. And this wave function doesn't tell us where the particle is. It just gives us the probability of finding it in a specific spot. So until you actually look, it exists in a superposition of all those possible values, all at the exact same time.
I know that sounds like a wild sci-fi theory, but it's actually grounded in incredibly hardcore math. Take this highly specific number on the screen, 364.56. This is Balmer's constant. Johann Balmer literally figured out an equation using this exact number in nanometers that perfectly predicted the visible light frequencies given off by glowing hydrogen lamps. The math proved that these electrons aren't just orbiting randomly. No, they are jumping between perfectly discrete, quantized orbits, and they emit highly specific frequencies of light when they drop back down. It's an incredibly rigid mathematical system for something so bizarre.
But as it turns out, that rigid math comes with a profound limitation. Werner Heisenberg captured it best. He said, the more we know about where a particle is, the less we can know about how fast it is going. Heisenberg proved mathematically that you just cannot simultaneously know both the exact position and the exact momentum of a quantum particle. Think about it. If you use a high-energy photon to see exactly where an electron is, you literally bounce energy off of it, which fundamentally changes how fast it's moving. And the craziest part? This isn't just because our microscopes are flawed. It's a fundamental, unavoidable limit built into the very fabric of the universe.
All right, moving on to part 2. The measurement problem. Why does looking change everything?
Okay, so we've established that the quantum world operates in this strange haze of probabilities that only lock into a definite state when we measure them. But man, does that create a massive philosophical headache. I mean, think about it.
Is the quantum state a literal physical element of reality, or is it merely a representation of what we know or don't know about a system? This massive debate, whether the quantum state is physical reality, which physicists call ontic, or just our own human knowledge, which they call epistemic, that is the absolute core battleground of quantum foundations.
Erwin Schrödinger, one of the founding fathers of quantum mechanics, actually hated this tension. To show everyone how absurd it was, he came up with his famous cat thought experiment. Basically, he imagined placing a cat in a sealed steel box, along with a radioactive atom that's in a quantum superposition of both decaying and not decaying. If it decays, a little hammer breaks a vial of poison, and the cat dies. If it doesn't, the cat lives. But, because the atom is in a superposition, quantum math insists the entire box is in a superposition. Therefore, until you open that box and make a measurement, the cat is simultaneously dead and alive. Schrödinger was basically shouting, "Look at this glaring flaw! How does a continuous reversible quantum wave suddenly just collapse into a single irreversible reality just because somebody peeked inside?"
And if you look at this visual map, you can really see how the scientific community has desperately tried to answer that exact question. The theories just splinter off in all directions. You've got the Copenhagen interpretation, which mostly just accepts the strange collapse of the wave function as a rule we have to live with. Shut up and calculate, as they say. Then you've got the mind-blowing many worlds theory. That one argues the wave never collapses at all. Instead, reality itself just splits into parallel universes for every single possible outcome. Oh, and then there are the de Broglie-Bohm pilot wave models, which suggest that, actually, scratch that, particles do have definite positions at all times, they're just guided by hidden, non-local waves. There is absolutely no consensus yet, just some incredibly fascinating possibilities.
Which brings us to Chapter 3, Einstein's spooky action, entanglement, and the breakdown of local realism. So the whole idea that reality was just probabilistic and undetermined until we measured it, Albert Einstein hated it. It deeply, deeply troubled him. And his frustration led to his most famous objection, which centers entirely around this concept, quantum entanglement. Remember superposition, where a particle holds multiple probabilities at once? Well, if you entangle two particles, they share that exact same probability state. If you then separate them, you could put one on Earth and shoot the other one all the way to Mars, they somehow remain connected. The absolute split second you measure the particle on Earth and find, say, an up spin, its entangled partner on Mars will instantly, magically snap into a downspin.
Einstein absolutely refused to accept this instantaneous connection. He famously dubbed it spooky action at a distance. For him, nothing, literally nothing, not even information, could travel faster than the speed of light. So he argued that quantum mechanics just had to be an incomplete theory. He firmly believed these particles weren't magically communicating across the galaxy. Instead, he thought they must possess some kind of hidden variables, like secret pre-programmed instructions they were created with. Think of it like a pair of gloves. If you open a box and find a left glove, you instantly know the other one is the right glove. No spooky communication required, right?
Well, in 1964, a physicist named John Bell came along and figured out a brilliant mathematical way to actually test Einstein's hidden variables theory against the spooky action of quantum mechanics. Researchers set up separated stations for two observers. Let's call them Alice and Bob. They sent entangled particles to both stations, and Alice and Bob measured the spin of their particles at varying angles. Now, Bell created a very strict mathematical limit, an inequality. He proved that if Einstein was right, and the universe relied on local hidden variables, the correlation between Alice and Bob's measurements could mathematically never exceed this specific limit.
So they ran the experiment, and you know what? They broke the limit. The results completely violated Bell's inequality, proving definitively that Albert Einstein was wrong. I really can't overstate how monumental this is for physics. It proved that our universe is fundamentally non-local. These spooky, instantaneous connections, they are not a math error. They are an absolute, verifiable reality of nature. Particles separated by vast expanses of space are somehow deeply, instantaneously connected. Mind blown.
Okay, let's zoom back out for Chapter 4, Real-Life Quantum Technology, the Macro Payoff.
Look, I know we've been down a pretty deep philosophical rabbit hole today, but these incredibly weird microscopic rules aren't just abstract academic puzzles. They are literally the engines driving our modern technological world. Check out how perfectly these bizarre concepts map onto things you use every day. We talked about how light comes in quantized packets called photons, right? Well, when those photons hit certain materials, they knock electrons loose. That's the photoelectric effect, and it's the exact reason solar panels can generate electricity for your house. The hyperspecific vibrations of atoms, we use those to build atomic clocks, which synchronize the GPS satellites that help your phone navigate. And that wild concept of superposition, being in multiple states at once, that is the exact foundational architecture being used right now to build revolutionary quantum computers.
And honestly, the list just goes on and on. Without a deep understanding of quantum mechanics, modern medicine and electronics would basically grind to a complete halt. Take MRI machines. They literally rely on detecting the quantum magnetic spin of atoms inside your body to give doctors non-invasive images of your organs. The semiconductor transistors inside the phone or computer you're using right now, they operate by strictly controlling the quantum flow of electrons. Even the laser scanner at your local supermarket checkout relies on stimulating atoms to drop their energy levels and emit identical concentrated photons. It's everywhere.
And the crazy part is, we are only just scratching the surface. The quantum future is going to be even more incredible. Remember the measurement problem we talked about earlier? How observing a system fundamentally changes it? Well, we're actually using that quirk right now to build quantum encryption. It creates literally unhackable cybersecurity. Because think about it, if a hacker tries to intercept and look at the data stream, the quantum state collapses, and the system instantly knows it's been compromised. We're also developing quantum dots for ultra-vivid screens and life-saving biological imaging, plus nanoelectronics that exploit quantum tunneling to push computing speeds to unimaginable new limits.
So as we wrap up this explainer, I really want to leave you staring at the ceiling tonight with this one lingering thought. We've seen the proof. The math works perfectly, and the technology sitting right in our hands proves that it works. But that huge foundational mystery still remains. If the simple act of observing the microscopic quantum world fundamentally changes it, what does that ultimately say about the reality we live in? Are we just passive observers in all this, or are we actively participating in the creation of the universe just by looking at it? Thank you so much for joining me on this journey. Keep asking those massive questions.